Hello and welcome to NCC Group's Cryptopals guided tour. My name is Eli, I'll be your guide. In this video we'll be looking at Challenge 11 from Set 2, in which our goal is to implement an ECB CBC detection oracle. Now before we go any further, let's take a moment to talk about that term, oracle. This is a term that we've used before and I kind of threw it out there like everyone knows what it means, which in crypto circles is pretty much true, but it might not be familiar to everyone. So let me just explain a little bit. An oracle is sort of like a function, but it's a function that you feel like being dramatic about. And as far as I can tell, the modern use of this term comes from the late, great Alan Turing, who used it to describe functions that, in his sense, really could not be computed without something analogous to divine revelation. The idea being that these are things that would be useful to know, but we're sort of setting aside the question of how you possibly could know them in order to look at what you could do if you did know them. The meaning has drifted a little bit in the intervening years between then and now, to the point where rather than implying a function that could only be evaluated with the aid of mystic revelation, it is now more commonly used to imply a useful function whose implementation is left deliberately unspecified. So in this problem, we have two oracles. One of them is an encryption oracle. You give it plain texts, it gives you ciphertexts, but crucially, it keeps the encryption process opaque from you. It doesn't tell you the key, or whether it's using ECB or CBC mode, or anything about the random bytes that it adds onto your plaintext before encryption. And we're calling this an oracle because how you go from messages to ciphertexts here is left deliberately vague. You know, this could happen in any number of ways. And the question here is, what do you do if this does happen? You know, given a tool like this, what can you do with it? The second oracle that we have is our detection oracle. This is the one that takes an encryption oracle as an argument and talks to the encryption oracle and attempts to determine whether the encryption oracle uses ECB or CBC mode internally. So we'll have to implement both of these oracles. The first one is pretty straightforward to write, and the focus of the problem is on figuring out how to implement the second one. Now, this second one might sound a lot like what we did back in Challenge 8, in which we detected AES in ECB mode. In that case, we were looking directly at ciphertexts rather than querying an oracle. But the way that we did this back then was by splitting the ciphertext into blocks and then looking for repeated blocks. The difference this time, of course, is that we actually have to generate the ciphertexts ourselves. For this problem, we as the attacker get to choose a message. We have an oracle that takes this message, modifies it, then pads and encrypts the modified message, and returns the resulting ciphertext. So as the attacker, we control some of this plaintext, but not all of it. Now we know that this encryption function uses either AES ECB or AES CBC, and our goal is to find something that we can do to our message that will carry through into the plain text and result in a property that we can look for in the ciphertext. So how do we do this? The answer might seem obvious to some of you, and indeed the solution that we'll end up using is very simple and very similar to Challenge 8, but there are a couple subtleties that we'll miss if we rush through it. So let's take things slow and talk it through as we go. The basic idea of what we want to do is this. We will make a message that is long enough to produce two repeated blocks of plaintext, no matter how long the random prefix is. If we do this right, we can, of course, completely ignore the random suffix, since it will fall after the second of our repeated blocks, and it will therefore have no influence on the blocks that we care about. So we'll conservatively assume that the prefix has a length of 5, which is the shortest length it could have, meaning this is the case where we need the maximal amount of padding in the first block. To be specific, we'll need 16 minus 5 equals 11 message bytes, all of which should have the same value, and then we'll follow that with 2 full blocks of repeated bytes. We are, of course, assuming a block length of 16 as usual. After this, the encryption oracle will add some stuff onto the end, first the random suffix, then some padding bytes, but what's crucial to see here is, no matter how long the prefix is, we should always have at least 2 blocks of repeated bytes in our plaintext. And depending on the length of the prefix, we might actually have a little bit more, a little bit of slop over the end here, but we don't really care about that. Now, if we make up some random values for the prefix, suffix, and IV, then we can check our work by running this message through each mode and seeing what we get. Now, this gives us a straightforward test that we can use to distinguish ECB from CBC. There is one more detail that I want to mention before moving on. We've been assuming that these are the ciphertexts we're getting, but what if the IV is prepended to the CBC ciphertext? This would not be theoretically correct behavior, but it's very common in practice. And if the oracle does this, then it does throw off our block indices. Luckily, this turns out not to matter, because it only applies in the CBC case, which is the case where we already expect these blocks not to be equal. So if we're comparing 2 different unequal blocks than we intended to, then the test will still succeed. However, if we were still bothered by this, we could always index into our lists from the end rather than the start by using negative indices, at least in Python, which would ensure that we're always looking at the intended blocks, no matter how many leading blocks the oracle adds. And also, just as an aside, if IVs are included in the ciphertext, then there's a second, simpler solution we could use. Looking at this figure, you might have some intuition for it. We can see that CBC ciphertexts will be longer than ECB ones for any given plain text. And you might think, surely that's exploitable. Well, if we had both ciphertexts like we do in the figure here, then it would be really easy to figure out which one's which. But in reality, we only get to query the mode that the encryption oracle actually uses, so we can get one of these, but not both. And furthermore, due to the random prefix and suffix, we don't know exactly how long the plaintext and hence the ciphertext will be. But what we can do is take the range of possible lengths for the plaintext and adjust our message length so that this entire range falls within a single block, like so. Now we just test whether the ciphertext has 2 or 3 blocks, which would indicate ECB or CBC mode respectively. This isn't really an honest solution to the challenge, so to speak, but dishonesty plays a large role in cryptography. It is, after all, a no-holds-barred sport, as we will repeatedly see throughout these challenges. And this solution is undeniably simple and efficient, whatever else you might say about it, at least in the cases where it can be used. If IVs aren't included in ciphertexts, then the solution doesn't work at all, which is why we'll be implementing the first solution rather than this one. And so without any further ado, let's get to it. And you'll notice something different in this screencast. I've decided to take the liberty this time around of writing this script in advance, and then I figured we'd just walk through it together rather than forcing you to sit through watching me type for, like 10 minutes. So let's just start at the top and work our way down here. So we have this function here which gets the encryption oracle. This is not the encryption oracle itself, but you'll see it creates a closure defining the mode that the encryption oracle will use. And then we define the encryption oracle down here and return both that and the mode together. Now this allows us to make multiple queries to the encryption oracle and have them use the same mode, but have the mode be randomly selected for each instance of the oracle that we retrieve. So this is not strictly necessary since we actually only call the oracle once, but this just seemed like good practice, in my opinion. The encryption oracle itself is pretty straightforward. We have the key, the prefix, and the postfix. These lengths are not randomly chosen, but neither do they need to be. Or excuse me, they are randomly chosen, but they're not cryptographically securely randomly chosen. And you can see that if we go into Python's random.py where this is defined, you can see that this is just a method of a instance of random, which is not system random. System random is the OS randomness source that we would actually trust for cryptographic operations. Although really in Python you should be using the secrets library if you care about that. But moving on, we take the prefix, plaintext, and postfix, concatenate them to create a new plaintext, and then create a padded plaintext with PKCS7. And then we encrypt that under either ECB or CBC mode, depending on the mode defined up here in the closure. And we return the result of that encryption from our oracle. And then down here, of course, we're just returning the oracle and the mode as we discussed. Now, the next thing up here is our... Oh, actually, before I get to that, let me just call out really quickly the type annotation here, because this is something that some people find unintuitive. This is a list containing all the arguments. In this case, there's only one argument, so it's a list of length 1. And then this is the return type. So it's really fairly straightforward, but might look a little weird if you're not familiar. And we're defining this as a name up here just because it's shorter and more legible to use this name. And we're using it in both of these annotations, so it's in 2 places. And you want to highlight that it's the same annotation in both places, which also wouldn't necessarily be obvious at a glance if you're looking at something like this, which is a little bit more opaque. And then likewise with the block size and key size here. Key size of 32 isn't really necessary. 16 would be fine, but I just enjoy using bigger keys. You could make an argument for smaller ones on performance, I think, although I actually don't recall quite what the benchmarks look like there off the top of my head. Anyway, moving on, our detector function here takes a oracle and then runs the attack that we discussed earlier on in this video. We generate 2 full blocks plus a partial block of null bytes. And so we're just taking block size -5 here because that is known to be the minimal possible length of the prefix. And so this guarantees us at least 2 full blocks of null bytes. And we get a ciphertext by passing this plaintext to the oracle. And we break that ciphertext into blocks. And we compare the blocks. It's as simple as that. And if we really wanted to go all out here, instead of returning strings, we could define an enum Or we could return, AES.mode ECB versus AES.mode CBC, things of that nature. We don't have to use strings here, but personally, I think this reads better. Although, you could make an argument for doing it other ways as well. But moving on to the very end of the script, I just figured, what the heck, rather than just testing it once, let's test it 1,000 times. So within this loop, we get our oracle, we get our mode, and note that the detector function here does not have access to this mode variable. This is secret. That's known from the calling code, but not from the detector. So we know that there's no tricks up my sleeve here. This is all honest crypto, figuring out ECB or CBC, and then we print the actual mode and the guessed mode, and if they don't match, we raise an exception. Otherwise, we have a little celebration and exit. Now let's run this and see if it works. And there we go, it worked. No exception thrown, and we can visually inspect all of these to see that they all match. So there you have it, that's challenge 11. I hope you found this helpful, maybe learned something, and I'll see you in the next one.